All right, so I just ended the last video. Okay, so this this was the discovery between the crust and the mantle. All right, because of course the mantle is more dense than the crust. That's why the crust rides on the mantle. We'll talk about that. Um, all right, so so the next person, this guy Gutenberg. Again, we don't care that much about their names. So this was all right around the beginning of the 20th century. Discovered that there was a location, you know, between the mantle and the core, right? Um, and this of course this goes back to Oldham's work as well. And what he realized was that when the P wave reached this depth of 2,900 kilometers, that there was refraction. Okay, so there's a nice picture right here. So what happens? Remember, the P wave can go through go through the liquid core. So this is the liquid core right here. And so first of all, notice we've got um, the let's see which ones are which. So the black lines are the P waves. Notice the S waves never go through the core part, right? Remember that's the thing that this guy Oldham discovered. All right, so but what this guy did, refining this discovery, is he found that that there were these regions of refraction of the P wave. So the refraction. So when the P wave hits the boundary, it'll refract, and so between 105 degrees and 140 degrees of let's say of the epicenter of the epicenter is where the earthquake took place. You would see this shadow region on the other side of the earth where you didn't see any S waves, you didn't see any P waves, right? So that but then once you got beyond that, you would start to see the P waves again. So there's this shadow right here is just because of refraction, that the bending of the P wave, um, right at the boundary. So that right at the boundary, just like when water or when light passes through glass, it'll bend. If here's a good example of this. You might have seen this in school at some point. If you take a piece of, you take just a clear glass of water and you put a pencil in the water, it looks like, just looking at it, it looks like the pencil is bent. Of course, you can take the pencil out and notice that it's still a nice straight pencil. And the reason that it bends is this phenomenon called refraction, because light is a wave and light will bend. Well, of course, these are waves as well. The P wave, it's a longitudinal wave, that's fine, but it also is a wave, and so the fact is that it'll bend, and so this 105 to 400 degree bend, where you don't detect any P waves, that helps us understand exactly how deep this region is. And so you find, you got to understand, like, this is not just one single, this is one of the things I always tell people. It's not just one single instance of an earthquake, right? I mean, there's earthquakes going on all over the world all the time. And so you always see this, from the epicenter. Imagine the epicenter was over here. On the other side, you'll see 105 degrees to 140 degrees, where you don't see any P waves, and that's because that they're in this shadow, because there's a refraction going on. All right. So anyhow, let's see. So they refract. Um, yeah, yeah. So that was what this guy Gutenberg discovered, which again, helps us understand, the size of the outer core. All right, but by his time, they didn't realize that there was an outer core and an inner core, but that's coming up. All right, so this guy comes along in 1926, um, and determines that the core or part of it must be liquid, and so this is the whole idea of um, that uh, that there's an what this guy discovers. Whoops, not this guy. This guy Jeffries discovers is that within the core, the P waves would they'd slow down and then they'd speed up and then they'd slow down again. All right, so that of course is like, imagine this. So over here they're passing through liquid, they pass through solid, and then they pass through liquid again. All right, so that's what this guy discovers. All right, so oops, went the wrong way again. Sorry about that. So this firmly established the idea that there's a crust, a mantle, and a core. All right, so what else? Actually, hold on. So what Jeffries, hold on, I think I got that wrong. So what Jeffries actually found is, but with the variation in speed, he realized that Jeffries, I'm talking. Oops, I'm at the wrong thing. Jeffries, where am I? Oh goodness, went too far. Here we go. Jeffries determined that the core was composed of, at least part of it was composed of a liquid. Um, that was important. All right. So then Ingo Lehmann comes along and observes that the P waves are also refracted at a certain depth within the core. At this depth, the P waves show an increase in velocity. So Lehman is kind of like the final step in determining that the core has two parts, right? So the guy before Jeffries just saw the slowing down and realized that there was liquid in the core. Okay, and then Lehman comes, a little while later, about 10 years afterwards, and she observes the fact that that not only is there a the liquid in the core, but she discovers that there's this speeding up that goes on as well. So there must be a solid inner core, right? So that was her work, and that kind of completes the picture that we now have of. Here, let's go back to the picture of the crust, right? So we have the outer crust, the mantle. And then the outer core, which is liquid, and then the inner core, which is solid. So that was the final thing. Yeah. In 1936, she discovers the inner core of the Earth. All right. So yeah. All right. So the core is primarily is composed of iron, and there's some nickel in there as well. Because of the density of iron and nickel, the core has two layers, of course, the solid inner core and then the liquid outer core. The inner core is solid because of the incredible pressure. The outer core is slightly less dense and will actually flow like a liquid. It is a liquid, sorry. So it flows. And actually, it turns out that this is a really important idea. All right. So let me try to get into this in a little bit more depth. Let me see what the next slide is. Oh, all right. The fact that it's liquid, right? You have this liquid iron and nickel. Now, iron and nickel are metals, which indicate that the outer electrons of this is just true about metals in general, right? You look at the periodic table, the left hand side of the periodic table is in the vast majority of the periodic table are metals, right? Anyhow, metals basically when they bond with things, they tend to give up their outer electrons, and so this liquid iron, moving around inside of the core in the fact that it's liquid means that these outer electrons that are in the iron are moving around as well. All right, so as these outer electrons are moving, that's actually when a charge. So the outer electrons are charged when a charge moves from one location to another. If it just moves, all right. So if a charge moves, you get a magnetic field, right? And in fact, of course, the Earth has a magnetic field. The magnetic field of the Earth comes from the outer liquid core of the Earth. And the magnetic field of the Earth, as we're going to find out, has changed over time. I mean, where the north, the magnetic North Pole is, well, so sometimes it actually flips. In fact, just recently, I read something where some geologists were seeing more and more evidence that the Earth's magnetic field might be in the process of flipping. I forget what it does. It averages, every few 100,000 years it'll flip. The sort of like the geographic North Pole, where Santa lives. That's of course that's currently the magnetic North Pole, but sometimes that magnetic North Pole is down where the penguins live, right, in the South Pole. All right, so let's see. So Earth has the inner layers. It's got the mantle, and then let's see. I guess we're done with the different names of people. All right. So I couldn't find who came up with this. It was probably just a group of people. Anyhow, this next thing is we're going to further examine the mantle, which, by the way, takes up, by volume, 82% of the Earth's entire volume, right? And 65% of the mass is this thing that we call the mantle. Now, so the mantle is this lower red. So notice we've already divided the mantle into, it's someone, I forget who it was, found that there was a boundary right here between the upper mantle and the lower mantle. The lower mantle, it acts more like solid rock. The upper mantle, which has this wonderful name, the asthenosphere. The asthenosphere. Okay, so that's what it's called. It acts more like a plastic. Okay, so that's and of course the mantle is very rich in silicates, which of course are silicon and oxygen. We talked about those back in chapter 20. And of course, and there's other stuff in there too. There has to, there's iron and there's magnesium and calcium and other carbons and silicates. Sorry. No, they're all silicates, but there's also like sulfur, things like that, sulfur dioxide, all sorts of wonderful things. So the main thing here is that it's got these two layers. The mantle, the upper layer acts like a plastic, and so there's really the convective currents rise, cool off, and then fall. It takes millions of years for the current to go, to complete one cycle. But what that does is that's causing the Earth to change, the crust of the Earth to change over time. All right, so the the crust right here, the